So this picture is showing perfusion of oxygen into the blood. And so this is technically tied to the previous video. Technically, this is part of your external respiration story. However, it's sort of related to the next topic as well, which is the transport of oxygen through the blood. All these things are tied together, as you know. You have to make the connections between topics. So in this picture, we start looking at the perfusion of oxygen. We start at 40 millimeters of mercury as the oxygen is approaching the lungs, and then as the air enters the lung, as the blood enters the lungs and makes its way around an alveolus, eventually the oxygen will be fully perfused into the blood, and you end up with a partial pressure of 104 millimeters of mercury by the time you are only a short time in the lungs. So as you can see, it only takes a quarter of a second, 0.25 seconds to reach full perfusion, as long as your lungs are nice and healthy. It takes about 0.75 seconds to make for the blood to make its way all the way to the end of the alveolus. So kind of take a look at this picture, study on it. We will be drawing this in class. So what happens next? The oxygen is in the blood, and now most of it is going to be bound directly to hemoglobin. In fact, 98.5% of oxygen is loosely bound to hemoglobin, and about 1.5% of it will be dissolved directly in the blood plasma. There's quite a lot to look at in this picture. So you can see the way that things work generally when we're transporting oxygen in red here and carbon dioxide in blue. Carbon dioxide can also be bound to hemoglobin, but in a much smaller number. Just so you know, carbon dioxide, there's about 200 milliliters of carbon dioxide on average produced by your body every minute. 7 to 10% of it will be dissolved directly in the blood plasma. About 20% of it will be bound to hemoglobin, especially when oxygen dissociates from hemoglobin. Carbon dioxide has a better opportunity to bind, although you can see that it is not the main way that carbon dioxide is transported. About 70% of carbon dioxide is going to be transported as bicarbonate ion, and that is this equation right here. We're going to be taking a look at this equation more. Carbon dioxide, when it is present in water, especially in the presence of carbonic anhydrase, will become carbonic acid. Carbonic acid can then dissociate into bicarbonate ions, and look at that, hydrogen ions, which is acidity. And so we'll be looking more at this quite a lot when we're looking at the blood pH. All of these structures are relevant. Just so you know, carbonic acid is a weak acid. Bicarbonate ion is a weak base. So they both serve as buffers for this system.